Gauss's law in differential form. Okay. So now let's try another flux integral. And this was another one of these cases where we're going to do it in such a way that we avoid the actual vector calculus. We're going to do it geometrically. I'm going to do a cube, or not a cube, rectangular prism. Let's say I have this region of charge. They are charges all over the place. Maybe there's some negative ones over here, some positive ones. It's described by a charge density, volume charge density, as a function of x and y and z. And what I'm going to do, I'm going to take a small rectangular prism. And this is going to be my surface area. I draw this with remarkable 3D precision. Good. Do you like that?
Yes.
Okay. And let's line this up with the coordinate system to make our lives easy. This will be the x direction, and I'll call this dimension delta x. And this will be the y direction. I'll call this dimension delta y. And this will be the z direction. I'll call this dimension delta z. Okay. Now, let's say I also am going to have a flux density vector field describing the coulombs per meter squared, the quantity that we've been working with over the last lecture period, as it is also a function of x, y, and z. So keep in mind, in this entire region, I'm going to have an electric flux density vector, which we all know in this class is really just shorthand notation for writing an x component stuck on the x hat unit vector plus a y component of the field stuck on the y hat direction, and the z component stuck on the z hat unit vector. Now, I'm going to say that this is a very small cube. Small cube such that the charge inside, this rho sub v as a function of x and y and z, it'll change as I move x, y, and z around. But inside here, it's approximately a constant. That's how small I made this. I'm just observing it over a tiny region of space. So I don't see too much change. And the same is true for some of these other quantities. Well, this is what we'll do. Let's set up our flux integral. I go over to this next pane. Conveniently, I don't even have to erase this top equation. Couldn't have planned that any better. The flux integral outside the cube, counting all the flux that goes into and out of the cube, must be equal to the charge enclosed by that cube. So let me evaluate those two things using Gauss's law. So I've got 6 sides of my cube, and so I should have 6 terms for my flux integral, my surface flux integral. I look at that first facet, the one pointing to me in my extraordinary 3-dimensional diagram that Lamb approves of.
Question.
Yes?
The field that we're talking about, that's not a surface area, that's a 3D field.
Yeah, that's right. This D field is defined in all points in space. And I guess technically so is rho sub v, but I kind of drew it like it's in this volume over here. Maybe it goes to 0 outside there.
I'm just talking about like the blob thing you kind of drew. It's enclosing the cube.
Yeah.
Okay.
And maybe it was even a little misleading to draw a blob there. The point is that there's charge in space.
Oh.
This is my blob of charge.
Okay.
It could be 0. We don't know. So what I'm going to do is I'm going to pick up the flux components here, coming into that surface, into here, up here, through here, and let's see, into here and out of there. So each facet gets a side. I got 6 terms here. So my first x facet, the one that is pointing in the positive x direction, the flux through there is going to be my d field, my x component of d field, and what's more, this is going to be evaluated at x plus delta x, because it's the far side of that, right? That's the total amount of flux, or the flux density coming out of that. And if I want the total flux, like I'm evaluating it across that rectangular surface and integrating it, then I have to multiply by the area of that surface, which is going to be delta y, delta z, right? Looking good so far, looking good. And that component, that's coming out by the way I define things. I'm going to subtract from that whatever's coming in on the other facet from the other side, the one that's kind of on the left-hand side, which is evaluated at x, y, and z, and has the same area, delta y, delta z, because it's the same rectangle on the other side. So, and the reason why that minus sign there is just I have to pick a convention for counting the flux. I usually do a right-handed convention, right, where this is x, this is y, and this is z, right? So these are all kind of like your positive directions. And so I'm defining my surface normal vector to point for the left-hand side in the positive direction. So that gives me a net positive when I count that flux. When I go to the other side of the cube, I'm pointing in the opposite direction. So my d coming in is opposite. That x component is opposite the surface normal on that other side. Okay, so that's my first 2 terms. That's basically 2 of the 6 separate integrals I got to write for a cube if I'm counting the total amount of flux through the surface. Now I got to do it for y too. dy at x, y plus delta y, z, and that facet is, let's see, that's going out that way. So that dimension is delta x times delta z. And of course I got flux coming in the opposite end, which is dy evaluated at x, y, and z, also with that same area.
Is it added to the previous set of terms?
That's right, that's right. I should put a plus there to make sure we got this. So this is rectangular prism surface number 1, 2, 3, 4. I got 2 more I got to write. Now let's do the z component. I got one coming out the top. And that's evaluated at z plus delta z. And I got some coming in the bottom. I got to change the sign and count the net change there. So that is d sub z as a function of x, y, and z on that side. Delta x, delta y. And that equals to the total amount of charge in that cube. As it's not really a cube, it's a rectangular prism. So the volume is delta x, delta y, delta z. And we got the coulombs per meter cube volume charge density there. So first of all, I got this equation, this nasty equation, that at least I was able to integrate with or without doing any real calculus. The net flux through the x direction, the net flux through the y, and the net flux through the z. And to simplify, I'm going to divide both sides by delta x, delta y, delta z.
Professor Berry?
Yes.
I'm not understanding something.
Yeah, what?
If you're doing dx in respect to x plus delta x, and then you minus dx in respect to x, why don't you just evaluate dx in respect to delta x, y, and z, and then you wouldn't have to do this. I'm not getting it.
Let's see. What we're physically saying here is that we're looking at the x component, because that's the part that's normal through the field facet, or the facet of that prism. And we're evaluating it on the far side, which is x plus a little bit. And then we're going to count the flux coming in the other side, too, which is just x.
Right.
And then we multiply by the surface area. So we're counting the amount that comes in and the amount that goes out.
So why not just do a little bit?
I don't get it.
Never mind.
What if there was a lot that came out?
Then this term would be really big and this term would be really small. Yeah, so it kind of accounts for that. Oh, yes?
You said you were going to do something to both sides of the equation. What's the other side?
Oh, yeah. Okay, so to finish off my thought there, I'm going to divide both sides by delta x, delta y, delta z.
There's a bunch of terms there. What's the other side of this?
This.
Okay.
This is the equal sign. This is the stuff on the left side. This is the stuff on the right side.
I didn't know what you were saying. All of that was equal. It was just the change in all of them. Okay.
Yeah. This guy is this.
Okay, that's what I was asking.
This guy corresponds. It gets kind of hairy when you get multiple lines on the board.
Oh, okay. Now I understand. See,
Yeah, no problem. Okay, so I've been waiting to do this for 5 minutes. I'm going to divide both sides by delta x, delta y, and delta z. Which means, okay, this side had delta x, delta y on both terms, which means I just have a delta z left when I divide through. This group of terms had delta x, delta z. I'm just going to have a delta y left when I divide through by both terms. This one, delta y, delta z. I'm going to just have delta x when I divide through by both terms. And then, of course, I like to be exact here. We said that we were looking at a case where we had a very small rectangular prism. Let's go ahead and just take the actual limit of this thing. As delta x goes to 0, delta y goes to 0, and delta z goes to 0. Which, of course, why would I do such a thing? Because that's the definition of what? Derivative. That's right. In fact, this is a multivariable problem, so these are partial derivatives. We're holding, in this case, we're taking the partial derivative with respect to x while holding y and z constant. And we're doing the same thing with respect to y and with respect to z down here. So more elegantly, I can write this equation as partial derivative of my x component of flux density, which we always have to remember is a function of x, y, and z with respect to x, plus the partial derivative of the y component of electric flux density with respect to y, plus the partial derivative of the z component of electric flux density vector with respect to z is equal to volume charge. Well, let's just make sure that we did this dimensionally correct. What are the units of d? Coulombs per meter squared. It's a flux. Charge per meter squared. I just took the derivative, which means I've now got charge per meter cubed, a volume charge density, and that's exactly what I have over here. That's always a good sanity check to go through. In fact, this is a nice little elegant formula. I can write it even more elegantly using my vector calculus formula. Look at this. Savor this moment. The first time we've had to use a vector calculus operation, differential operator, in our class. I'm enjoying it. Are you? No? Oh, yeah. All that work just to get that. So this is actually Gauss's law in differential form. It means the same thing as the integral form. In fact, this is one of the Maxwell's equations, one of Maxwell's 4 fundamental equations. This is important stop 1 in our tour of Maxwell's equations that we're doing. We often say that this is the differential form. We'll also call this the point form, because it basically says the divergence of my electric flux density, which of course in this class is always proportional to electric field, is equal to my charge density. So a lot of people, when they see these vector operators, they get a little bit scared and confused, and it's kind of hard to imagine. I'll teach you how to imagine this in a second. First of all, just to review, what does the del equal? This is the del operator. The symbol is an upside down delta that we call a nabla, if you're a typesetter. Has anybody heard that term before? Nabla? Upside down delta? Nabla, I think, is Greek for harp. Kind of looks like a harp, right?
Yeah.
Yeah. Yes, you see it. You see it. He's with me. He's with me. Yeah. Don't criticize, Lamb. I know it's not that good of a harp. So we got this nabla, and the nabla is equal to partial derivative with respect to x as an operator stuck on the x hat unit vector, partial derivative with respect to y, stick it on the y hat, partial derivative with respect to z, stick it on the z hat. And this winds up being a wonderful shortcut to writing this longer expression up here, because my d vector, which is really dx, stick it on the x hat, dy, stick it on the y hat, dz, d sub z, stick it on the z hat. These two vectors, this is really a vector operator. When you dot them together, of course, that means you take the scalar product of the x components, add it to the y components, add it to the z components. And in doing so, you effectively construct this partial differential expression. So that's what this divergence operator in vector calculus does. Remember, divergence always operates on a vector, and the outcome is always a scalar. And that's good, because this is always a scalar, rho sub v. It's charge density. There's no direction associated with it. It's just the amount of charge at a point in space. There is a direction associated with d, so it is a vector. It's proportional to the E field, which of course has both a magnitude and a direction in space that represents the direction an electron would travel if you put it there. Actually, a proton, technically, defined for a positive charge. So now the question now is, what does it all mean graphically? So here's the little memory hook and the visualization aid that will help you immensely through this class and beyond and other sophisticated vector calculus endeavors. But you got to promise me you'll never tell another EMAG professor, because it's embarrassing. Don't ever let it on that this is how you envision this, because it's shamefully simple. What does divergence mean? It means the divergence of a vector field, of any vector field, just mathematically speaking, is equal to the vector's sourciness. How sourcey is your field? What do I mean by that? Well, remember, sources make fields start and stop on sources. They start on positive sources and they end on negative sources. So if you see a field that's just kind of like wandering around, meandering, it doesn't collapse or begin. It just kind of spreads out and wiggles around. That is not a sourcey field. If you took the divergence of that field, it would be zero, mathematically speaking. If it was an electric field, then you know there wasn't any charges in that region of space. It was not a sourcey region of space. But keep in mind, you can use this. This thing shows up all the time in all sorts of physical sciences. Take the divergence of the temperature gradient. And that'll basically tell you where your heat sources are. How sourcey is your heat? Look at the way that heat is flowing. If the heat is just kind of moving around a solid object, not really going anywhere, not collapsing or increasing, if that heat flow, if that heat gradient is just moving around, then you know there aren't any heat sources, or cold sources for that matter, in your object. But if you see it all collapse down, it's pretty sourcey in that region. If you took the divergence, it would not be zero. It would probably be a big negative number if it was collapsing down. Likewise, if it was emanating out that vector field, the sourciness would be very positive in that area where it was coming out of. That's the geometrical interpretation. Now you never have to compute another divergence again, right? Well, you will in this class, but in your head, you know what it means. Sourciness. Sourciness.
Sourciness gives a direction? Or does it just give like a...
It just tells you what's there. So sourciness doesn't have a direction because when you take the divergence of a vector field, you get a scalar. So you don't know, you only know the net change in the flux and that through that one tiny region of space. There's no clue as to which direction the flux is changing. For that, you need another piece of information from vector calculus. In fact, there's a theorem in vector calculus that says that in order to specify a vector field, you can't just say what its divergence is. Because there's actually many different kinds of field that will give you the same divergence, the same sourciness. That's not true. If you specify the vector's curl and the divergence, then you've completely specified the vector field. Yeah?
So would divergence be a way of saying there's something here worth looking more into?
That's right. That's right. So for example, this is a really good example of how to use the divergence theorem. If you can take a little field strength meter and move it around in space and actually measure field as a function of 3D, multiply by the epsilon, take the divergence, all of a sudden you know where the charges are in that space. That's why we say there's a really good technique for undoing the field and doing the opposite of what we were doing in Coulomb's equation, looking at charge given a field instead of the other way around. Any other questions? Now, a couple notes about sourciness. A couple points that I want to make. Point number one, this gives us a really elegant way to express a mathematical concept. Remember how we said that enclosed surface integral of this vector field is equal to the volume integral of the charge density. And we just said here that the charge density is equal to the divergence of the D field. So now we have an equation relating D field to D field. And this is actually not an electromagnetics equation at all. It's a basic fundamental theorem of vector calculus. If I have a vector field, this here is called the Divergence Theorem. And it basically says that if I've got this integral where I count the amount of flux of that field through a surface area that encloses a volume, all I really have to do is take the divergence of that and integrate it across the entire volume, and I get the exact same thing, no matter what the field or what the shape of the volume. That's actually very powerful. And it turns out this is a very useful vector calculus relation, because there are some things that are very difficult to do as a surface integral. It's easier to convert them to a volume integral, calculate them that way, or vice versa. A very elegant mathematical theorem. So that's point number one that I want to make. This is the divergence theorem that we just kind of stumbled onto by doing our derivation that way. The other thing that I want to... Oh, yeah. Do you have a question?
How come the dV doesn't have a hat on it in the V area?
Well, because this is a vector. And that vector always points, you got to slide the direction around as you do that. Whereas this is just a scalar volume. So this will be your dx, dy, dz type volume integration. This will also have those kind of partial elements of integration, but they'll also have a unit vector stuck on the side of it as well. Okay, so that's number one. Point number two, and this is very easy to do. When we start looking at field quantities in other coordinate systems, for example, in one of the previous class periods, we said you could describe any vector in using spherical or cylindrical components and their corresponding unit vector decomposition. So for example, we could just as easily write D is equal to d rho on the rho hat unit vector, d phi on the phi hat unit vector, and dz on the z hat unit vector. And then we have described this in cylindrical coordinates. There are some types of problems with cylindrical symmetry where this winds up being an easier way to describe the field solution. Remember, the key difference, though, between this and the Cartesian system is that these can change depending on which point of observation you're at in space. So they are, in effect, functions of rho and phi. Which means when you go to take the divergence of this unit, of this vector field, this is a classic undergrad EM 3025 mistake. I always get a student, they get so jazzed up and so happy to do this calculation that I know divergence. I'm just going to take the derivative with respect to rho of the rho component, partial derivative with respect to rho, the rho component, partial derivative of the phi component with respect to phi, and partial derivative of the z component with respect to z. And I'm done. Where's that red marker? You must never do this. Never. Never. And this should immediately, most of you have probably already figured out why this is a bad idea, because this isn't even dimensionally correct. I've got coulombs per meter cubed, coulombs per meter squared per radian, plus coulombs per meter cubed. That doesn't even make sense. And the reason is that these things change as a function of position, unlike your Cartesian unit vectors. And therefore, you have to use some special formulas to actually calculate the divergence with respect to vector decompositions in other coordinate systems. Luckily, Haight and Buck has already done all the hard work for you. Anybody ever look? Do you have the copy of Haight and Buck with you? Anybody? Anybody even bought it yet? Good, good. Take a look on the back. Every cheat sheet formula you could possibly want is there. So let me give them to you so you have them in your notes. So Professor Durgan on a test gives you a problem where you got to take the divergence of something in cylindrical coordinates.
Dr. Durgan?
Oh, yes.
I just let you know that your red marker doesn't show through the...
Oh, yeah, it doesn't normally. It was a really thin one, and you probably couldn't even tell it was red. Unfortunately, there weren't any other red markers. So,
Oh, okay.
make sure, did everybody catch that in the video, that that was a really bad thing that I wrote on the board, and it should be X'd out? Okay. Okay, let's go over to this board just to emphasize. Terrible. Don't do that. Don't do that. Yeah, I got to be careful what I do, because some of that stuff doesn't show up on the video. Thanks for reminding me. Yeah. Oh, no, that's okay. We don't need to overdo it. Okay, so Professor Durgan gives you a cylindrical coordinate vector, and you take the divergence. How are you going to do it? You look on the back of the test, where all the formulas are, or on the back of Hayden Buck. And it's 1 over rho, partial derivative of rho times my rho component of my field. So I basically, instead of taking the derivative of just the partial derivative of just the rho component, I got to multiply by rho first, then take the derivative, then divide it out. So you see the product and then subsequent dividing it out winds up giving you the same units as just taking the derivative of d sub rho. But this accounts for the fact that changes far away from the z-axis are emphasized in the derivative, and then you kind of pull them out when you divide that out. So that's the first component. Then it's 1 over rho partial derivative of the theta phi component with respect to phi. And then I just got a regular old partial derivative of the z component with respect to z. Spherical coordinates. If I give you a problem in spherical coordinates where you got to take the sourciness, I mean divergence, then the way I write that, I got to do 1 over r squared, partial derivative with respect to r taken twice. Taken once, excuse me. R squared d sub r plus 1 over r sine theta, partial derivative with respect to theta, d theta sine theta, plus 1 over r sine theta, partial derivative of the phi component with respect to phi. And there we got it. And if you're in Cartesian, of course, you all have that one memorized already from your previous classes, I'm sure. So any questions so far? Nothing? Okay. So now we know how to go from charge to field and from field to charge. Our next topic, we're going to introduce the context of an electrical potential function, which winds up being a really helpful tool for doing our electrostatic analysis, because it's a scalar electric potential that actually has a lot of the behavior of the fields wrapped up in it. Sometimes it's easier to calculate that than it is to calculate your E fields directly. And it kind of jives nicely with our circuit understanding of voltages. that we use to analyze things like our transmission lines and all. So we'll do that, and we'll work some examples, and I may even dust off something. We'll look at some really arcane technology as an example, and some real cutting-edge technology as well to illustrate why these are really good things to know. So anyway, we don't have enough time to start a new unit, so I will see you on Thursday. Oh, yes?
Is that supposed to be r sine theta?
No, this should be r sine theta. And this should be r sine theta as well. Turns out both of them are on there.